Hello, this is the second video of the fifth complex number series on complex roots for the OCR Pure Core Further Mathematics, and it looks further at the nth roots of unity. In the previous video, we looked at solving z to the n equals 1 and saw in the GeoGebra program and slides that the roots of unity lay on a unit circle and were the vertices of a regular polygon with n sides. For example, for n equals 3, an equilateral triangle, as shown in the diagram below, and for n equals 4, a square, as shown in the diagram below. So in general, the roots of unity all lie on a unit circle centred on the origin, with one root at 1. As the modulus of z to the n equals 1, then every root of the equation z to the n equals 1 must have unit modulus, which makes sense if they all lie on a unit circle. It also means that every root may be written in the form z equals cos theta plus I sin theta, the modulus being just 1. Using de Moivre's theorem, which we looked at in the previous series, z to the n equal to 1 equals cos theta plus I sin theta all to the n, which equals cos n theta plus I sin n theta. This implies that n theta must be 2k pi. So we know the equation z to the n equals 1 has exactly n roots, and now we know that these can be written as z equals cos 2k pi over n plus I sin 2k pi over n, where k takes the values between 0 and n minus 1. These are called the nth roots of unity, and obviously include z equals 1 when k equals 0, and z equals minus 1 if n is even, i.e. when k equals n over 2. We have a look at this example where we're looking at z to the 6 equals 1. Then we can see that here is that root for k equals 0, z equals 1. And then the other roots would be, k equals 1, k equals 2, k equals 3, 4, and then 5. We use the Greek letter small omega for the root with the smallest principal argument. So omega equals cos 2 pi over n plus I sin 2 pi over n. Then by de Moivre's theorem, omega to the k equals cos 2k pi over n plus I sin 2k pi over n. And the nth roots of unity may be written as 1 omega, omega squared, and so on up to omega to the n minus 1. And as we've seen in previous series using GeoGebra, may be represented on an Argand diagram as vertices of a regular n-sided polygon. So for example, for n equals 8, we would have that omega equals cos 2 pi over 8 plus I sin 2 pi over 8, which obviously then the 2 pi by 8 cancels down to pi by 4. So this would be omega. Omega squared would then be cos pi by 2 plus I sin pi by 2. Obviously this one here, and so on. We would have omega cubed, omega to the power 4, to the 5, to the 6, to the 7, and remembering that the other root is 1. The sum of all the nth roots of unity is a geometric series with common ratio omega. You will note that A equals 1. And you are expected to be able to explain why the sum of the roots of unity is 0. Well, the sum Sn equals A 1 minus r to the n over 1 minus r. Remembering that omega to the n equals 1, then we'll know that 1 minus omega to the n must therefore equal 0, which therefore implies that s to the n equals 0 for all n. In the next video, we consider the nth roots of any complex number.